Lithium-ion batteries were first commercialized in the early 1990s and are now the dominant mobile energy storage technology. In lithium-ion batteries, lithium ions move back and forth between two electrodes. One electrode is composed of graphite, a conductive form of carbon that is arranged in stacked sheets, like in a deck of cards. The lithium ions are stored in between these sheets. So far, this is the method of choice, as other methods have proven to be much more unstable, causing the battery to fail in an unsafe manner. The second electrode is coated with another material that can accept the lithium ions as they shuttle across during discharge. The most common material used is nickel manganese cobalt oxide, NMC. Movement of positive lithium ions between these two electrodes is necessary as it balances the equal flow of negatively charged electrons as they move through the external electrical circuitry to which the battery is attached. Both flows together allow the battery to function. While this technology has been essential for powering phones, laptops and other mobile devices over the past 30 years, for more demanding applications like electric vehicles, the existing technology cannot deliver market demands. This is because currently used materials have fundamental limits on how much energy they can store in combination with lithium ions. Because of this, research has focused on finding alternative materials, particularly in the case of graphite electrodes, as they are one of the main bottlenecks that prevent more lithium from being used and therefore from more energy being stored. One of the most promising of the new materials is silicon. Silicon can store about 10 times more lithium ions than graphite. In practical terms, this translates to silicon-based lithium-ion battery packs being able to store at least 50% more energy per kilo than the best graphite-based lithium-ion batteries. Just like graphite expands as the lithium ions are accommodated in between the graphite sheets, silicon also expands as the lithium diffuses into it, during a process called alloying. In fact, silicon can reach up to 3 times its original size, much more than graphite, because it can store just so much more lithium. This very large expansion can cause it to crack and damage the electrode coating. Current methods for managing this problem are often expensive and time-consuming from a manufacturing point of view. This could make silicon appear to be an unviable solution. Gelion's proprietary silicon additive composites solve these problems by being really small, a few billionth of a meter. These so-called nanoparticles are what make up our silicon electrode. At this scale, the material exhibits different properties and is, in a sense, more elastic, which reduces the risk of cracking. The movement of lithium ions into and out of these silicon nanoparticles is easier than is the case when using graphite. The overall composition and construction of Gelion's particles help to make the batteries safer than current lithium-ion batteries while increasing their storage capacity. Silicon metal is predominantly produced by the metallurgical reduction of sand with coke, yielding a somewhat impure product. There are many processing steps needed to make battery-grade silicon particles, especially when nanostructuring them. Some silicon nanoparticles cost over $1,000 per kilogram, with precisely nanostructured high-purity battery grades costing up to $10,000 per kilogram. Gelion has exclusive rights to a patented process that converts simple raw materials into battery-grade nanostructured silicon particles in a single step. This means Gelion has access to high-quality silicon nanoparticles, which provide an innovative path to delivering higher energy density and improved safety at a fraction of current costs.